This video we are going to discuss on data structures and algorithms. Data structures, they provide a way to store and manage large amount of data. They enable fast and efficient retrieval of data. And especially we are going to discuss on trees and binary trees in this video. The agenda of this presentation is terminology, types of trees, representation of binary trees in memory, creating a binary tree from a general tree, traversing binary tree and its applications. Let us see the terminologies of the tree data structure. And here is an example of a tree which consists of several nodes. Nodes in the sense the letter which are marked with a circle we call as a node here. And the line joining the nodes we call as an edge. And in a tree, there is a specially designated node we call as a root node. So as far as this tree is concerned, here A is a specially designated node which we call as a root node. And B and C are children of the node A. And A is the parent of B and C. And also you can say B and C are siblings. The node which does not have any children are called leaf nodes. And as far as this example is concerned, I, J, K, F, G and H are leaf nodes. And root node is marked in level 0 and next children are marked in level number 1, level number 2 and level number 4 and so on. Hope you have understood the concept in general tree. And here when you take this tree, D is a parent, I and J are children. Okay. And this is a subtree for B. Here are some definitions. The topmost node of a tree or the node which does not have any parent node is called the root node. Topmost node of the tree, a node which does not contain a parent is called as a root node. Here A is the root node of the tree. A non-empty tree must contain exactly one root node and exactly one path from the root to all other nodes of the tree. The next one is parent node. The node which is an immediate predecessor of the node is called the parent node of that node. B, which is a parent node of D and E because it is an immediate predecessor. Then child node. The node which is the immediate successor of the node is called the child node of the tree node of that node. Example, D and E are the child node of the node B. Leaf node. The nodes which do not have any child nodes are called leaf nodes. This example is concerned I, J, K, F, G and H. They do not have any child, so these nodes are called leaf nodes. Ancestor of a node. Any predecessor nodes on the path of the root to the node are called ancestor of the node. A, B are the ancestor of the node D. Okay. Any predecessor node on the path from the root node to that node are called ancestor of that node. So here A and B are ancestor of D. Descendant. Here it is given a node X is a descendant of any other node Y if and only if Y is a ancestor of X. So from this you can say D is a descendant of A and B because A and B are ancestors of D. Sibling. Children of the same parent node are called siblings. Children of the same parent. D is a parent, I and J are children. So I and J are called siblings. Similarly, B is a parent, D and E are siblings. Level of the node, the count of edges and the path from the root node to that node. That is, the root node has level number 0, and you can have the levels as given in the diagram. Internal node, a node with at least one child is called internal node, and E is an internal node. Subtree, any node of the tree along with its descendant. For example, when you take this tree, this is called as a subtree. Along with its descendant is called as a subtree. And let us discuss on types of trees. There are many types of trees. Let us discuss on few of those. General trees. The general tree is a tree in which each node have either 0 or many child nodes. It can it cannot be empty. In general tree, there is no limitation of the degree of the node. Degree in the sense number of children a particular node can have. Next one is forest. A forest comprises several independent trees. They do not share any nodes. Then binary trees. A binary tree is a hierarchical data structure in which each node has at most two children. Each node has at most two children. And they are referred to as the left child and the right child. Next one is binary search tree. The binary search tree is a specialized type of binary tree that maintains its element in the sorted order, enabling efficient search, insertion, and deletion operations. The next one is an expression tree. It's a specialized binary tree used to represent mathematical expressions. Each node of the tree corresponding to an operator or operand, making it an effective structure for evaluating the expression, mainly used in compiler design. The next one is a tournament tree. A tournament tree is a complete binary tree where leaf nodes represent players and internal nodes show the winner or losers of the matches. The types of trees are illustrated over here. General trees in which a node can have any number of child. Okay, this is the general tree. And forest in the sense you can have more number of trees. And there is no relationship between this tree and this tree. Binary search tree in the sense a node can have at most two children. It cannot have more than two children. Here in this example is concerned the node 1 which has 3 children. This is not permitted in binary trees. And this is a binary search tree. Binary search tree is concerned it follows some order I said. So the root node is 8. The values in the right side is greater than 8 and the values in the left side is lesser than 8. When you take 8, it is 10 and here it is 3. 3 is lesser than 8, 10 is greater than 8. And similarly when you take 3, 1 is lesser than 3, 6 is greater than 3. And this is a ordering followed in binary search tree. An expression tree where every node that represents an operator or an operand, and this will help you to evaluate the expression. Tournament 3 leaf node represent players, and when you take this 1, 7, 3, 5, 2, 6, 4 and 8 are and player here this is a maximum winner tournament tree. So 1 and 7 is concerned, 7 is the maximum number, so 7 wins. 3 and 5 is concerned, 5 is the greater number, 5 wins. And similarly 2 and 6 is concerned, 6 is the winner. 4 and 8 is concerned, 8 is the winner. And the next level, 7 and 5, 7 wins. 6 and 8, 8 wins. 7 and 8, 8 wins. This is a tournament tree. Let us see how to represent the binary tree in memory. There are two primary ways to represent binary trees. One is linked node representation and the second one is sequential representation. In the linked node representation, each node contains data and pointers to its left and right children. Left of K contains the location of the left child of the node K. Info of K contains the data at the node K. Right of K contains the location of the right child of the node K. Let us take an example. Here is the binary tree, an A which has left child B, right child C, and similarly B which has a left child D and right child E, and the C node which has a right child F. In the linked representation, A node, so it has three compartments, one representing left, another one representing right, and the next one which represents the data. So middle one which represents the data and which left one which gives the link or address where the left node left tree is saved. So which is pointing to the left child and B, and here we have a pointer which is pointing to the left child of B. Similarly, B, there is a right pointer which is pointing to the right child of B, and this is a linked representation. In the sequential representation of a binary trees are concerned, nodes are stored in a one-dimensional array where the position of each node in the array reflects its position in the tree. Let us take 3 as an array and the nodes are stored in an array. First node A is stored in the first location. Left node is B which is stored in second location, and the right node C is stored in the third location, and again it is coming to the left D, and B node, it does not have any right child, so there is a dash in it, and so on. And here they said if a node occupies tree of K, then its left child is stored in tree of 2 into K, and its right child is stored into tree of 2 into K plus 1. That is, if C is stored in the location number 3, then E is stored in 6, F is stored in 7. That is what they said. So it is C is stored in 3, it is 6, and this is 7. So let us see how to create the binary tree from the general tree. Here is the rules for converting a general tree to a binary tree. Note that a general tree is converted into a binary tree and it could not be converted into a binary search tree. Rule number 1, root of the binary tree equal to root of the general tree. And here is the general tree, here is the binary tree. Root of the general tree A is the root of the binary tree. Left child of the node equal to leftmost child of the node in the binary tree in the general tree. And this is the leftmost node, that is the left child of the root node in the binary tree. Then the right child of the node in the binary tree is the right sibling of the node in the general tree. That is, we have to take the right sibling of the node in A. So there is no right sibling for A, so it does not have any right child. So root node you have taken as such. Left node in the binary tree is the left node of this node that can be taken. For the right node, it is the right sibling of the node A. Let us see now. Uh, so we have got the node B. For node B, you can take the leftmost node as a left node. But you cannot take this F as a right node. Instead, you have to take the sibling of B. Sibling of B is C, that is taken over here. Since A has no sibling, here I have not written any right node. Okay. Coming to E, E has no left node, so there is no left. Then we have to go for the sibling of E, which is F. That is the rightmost right node. Then, so we have processed all the node. D is left behind. That will be taken as the right node of F. Hope you have understood. So let us see traversing in a binary tree. There are 4 types of traversal in binary trees. One is in-order traversal, in which we'll travel to the left tree, then we'll follow onto a route, then go for right. In the pre-order, we'll visit root node first, then we'll go for left tree and right tree. In the post order, we'll go for left, then we'll go for right tree, then we'll meet root tree. The level order will visit all the nodes at the current level before moving to the next level. Let us consider the binary tree. In order, in the sense we have to move towards left. So you cannot move further, so you have to write D. Then the root node of D, that is B. Then you have to go for the right node, which is E. Then backtrack and move to the root node of B, which is A. Then go for right node C. This is in order. I'll repeat. Move to the leftmost tree until you are no further, could not be moved. So here we have D. Then root node of D, that is B. Then right tree, that is left root right. Left root right. Then all these 3 nodes we have visited. So these are the left tree of A. So left tree is written, then you are going for A. Then right. Left root right. Similarly, in the pre-order, you have to visit the root first, A. Then all the left tree. Okay. Root A, B is the root of this tree, then D. Left, right. So A, B, D, E. A, B, D, E, then finally the right node, right tree. Post order in the sense left, right, and the root node. So coming down, left, D, E, B. Then C and A. Root in the sense, root will be visited at last. So coming down, and D and E are left and right, and this is the root for these two. So D, E, B. Then you are visiting right, then you are going for this root node. Then level order. Level order in the sense, this is level number 0. So A is visited. Level number 1, B and C is visited. Then level number 2, D and E are visited. Hope you have understood. Let us conclude with applications of trees. There are so many applications of trees. Trees are used to store simple as well as complex data. Here, simple data means integer, character, floating point numbers, and complex data means a structure or a record. Trees are often used for implementing other types of data structure like has tables, sets, and maps. Another variation of tree, B trees, are prominently used to store tree structures on disk. They are used to index a large number of records. B trees are also used for secondary indexes in databases where the index facilitates a select operation to answer some range criteria. Trees are an important data structure used for compiler construction. They are also used in database design, used in file system directories. They are also widely used for information storage and retrieval in symbol tables. And hope you people have understood trees and binary trees concept. Thank you. Thank you for listening.